here we will have Martin. He's a software engineer based in Amsterdam, and he's also a Django Girl coach. He came all the way down here in Italy, and this is actually his third PyCon, so please welcome him. And he's going to tell us about why Unicode is still so difficult. The stage is yours.
Okay, thank you. Can you hear me well? Okay, awesome. Well, thanks very much for coming, everyone. If you're wondering if you've come to the right place, this is not about physics and string theory. This is actually just programming. So it could be worse. So my name is Martin Matusiak. I will be talking to you about strings, and I will be trying to convince you that strings don't actually exist. We'll see why later on. If you have any feedback on the talk, I would love to hear from you. You can ping me afterwards, or you can ping me on Twitter if you want. If you want to follow along with the slides, you can find them at this URL. But first of all, who am I and why am I talking about this? So I discovered Python about 10 years ago. I was really surprised to find a language that, even though I was dealing with an existing code base, it seemed like I could read it and understand what's happening, even though I had never ever explicitly studied Python. So that was a really novel idea to me. And I've been a big fan ever since. I worked a lot on web applications, and later on transitioned more into web services. I spent the last couple of years working at Amazon Web Services, working on corporate email. And then a little while ago, I decided to leave and start this startup company, which is called Ginger Payments. So what we do is payments online, which means that if you have an online business and you need to accept payments from your customers, that's something that we can help you with. We're also hiring, so if you like the idea of working at a cool startup company in Amsterdam, come talk to me afterwards and I'll tell you all about it. Literally, the coolest thing I know about right now in the Python and Django community is called Django Girls. So if you're not familiar with Django Girls, what we do is we organize a one-day workshop for complete beginners, and it's targeted at women. And we want to give them a really positive first experience with programming, and we teach them Django, and we teach them how to build basically a web application in one day. So I've been a programming coach at Django Girls a number of times. In fact, if you're going to be there tomorrow at this PyCon, I will see you there. And earlier this year, some friends of mine and me, we decided we wanted to organize one of these things. So I've also been an organizer of Django Girls in The Hague, where I live. So with that out of the way, let's talk about strings. So it might seem like a strange claim to make that strings don't exist, given that we all use them in our programs all the time, every day. Now, if you look at some strings, typically when we look at files, we open them in a text editor. And then we look at the file, and the content is text, and we scroll through the file, and we edit the file, and we have this very strong sense that what we're actually dealing with is text. Now, if we open a text file with a hex editor, which is what I did here, you kind of see that most of the screen is occupied by just like the bytes that are in the file. That's what the numbers are. And then almost as a bit of a footnote, you can see like the strings in the file. Now, you might seem that this is sort of an unusual way to look at a file. But what I want to suggest to you is that it's actually the bytes that are the content of the file, and the strings are the interpretation of those bytes. This might seem like it doesn't really matter. This is actually a really important distinction. So if you get that, then you're totally on the right track. So the strings are the interpretation of the file, of the content of the file. So obviously, strings are composed of characters. Characters are the building blocks of strings. There is this kind of funny situation because the relationship between characters and computers is a kind of difficult one because computers don't have a way of representing characters natively. If you open your computer and you rummage around in the hardware, there's no way that you will ever find something like the character storage unit, right? That doesn't exist. So if you want to be able to store characters in a computer, you have to kind of perform a bit of a workaround. You have to define, okay, what are all the characters that we may want to use one day on a computer? And then you give each one a number, and then you're going to store the numbers in the computer, all the while remembering that they're supposed to represent characters, right? That's what's happening. Again, it may not seem like it would matter all that much, but it turns out that this is really the source of all of our problems. So let's talk about Python. So in Python, we write characters this way. We have the P in quotes. In order to spell Python, we have to start with the P. And then we use the U prefix. So we're telling Python, I want you to treat this as a character. More specifically, this is a Unicode character. We have the same version in Python 3. Again, we can write the P in quotes. We don't actually need the U prefix this time. We can still use it if we want. Both of these forms are the same in Python 3. And we'll cover much more about the differences between Python 2 and 3 later on. So now we have this character. And what we want to find out is, let's say this character is part of a program that you've written. Later on, you want to run the program. Okay, so the program is running. That must mean that the program is now in memory somewhere. And if the character is part of the program, the character itself must be in memory. It's just logical deduction. And so what we'd like to know, would be kind of curious to know, is if we were able to track down exactly that memory location where this character is, what would we find there? So without actually checking, there are a couple of things we can figure out already. So first of all, it must be a number of some kind, because numbers are the only thing that we can store. But one thing to realize is that instead of this particular character, we could have stored any other character in this memory location. So the number that we're looking at has to, in some sense, be able to identify this character as opposed to all the other characters, right? So we need a notion of, like, what are all the characters? And this is what we call Unicode, right? So Unicode is this grand initiative to define all of the useful characters that we may want to use now or in the future. You can imagine it as this huge table where each of the row is a character and its number, and then the next character and its number. And in fact, we have over 1 million of these rows defined. In fact, the thing about Unicode is that while all of these rows have already been filled in with and assigned the numbers, not all the characters have been filled in. So there's actually plenty of free space, so to speak, in Unicode to add new characters before we'd have to adjust this limit. But so if we're going to store any of these characters potentially in a computer, we have to be able to use a number type that's big enough, right, to store both the smallest character and the largest character and anything in between, right? So if you think about what kind of options we have, if we start with just 1 byte, we're going to store one character as 1 byte. That gives us 8 bits, means we can store 256 characters. It's clearly not going to be big enough to store anything that may exist in Unicode. If we go up to the next step, that's going to be 2 bytes. So that 16 bits gives us 65,000 different numbers, therefore 65,000 different characters as well. Next step after that would be 3 bytes, gives us 24 bits. With that, we can actually store 16 million different numbers. So this would be more than enough to cover all of Unicode, both the way that it is now and probably even in the future. Now, it turns out that quite often in computers, we just like to use even numbers of bytes. So it's much more likely that we're going to end up using 4 bytes than 3 bytes. So with 4 bytes, that's actually 32 bits. We can store 4 billion different numbers. So that's more than enough to represent all of Unicode. OK, so back to the question. So we have this character. What does it look like in memory? If we were actually able to figure out the location of where Python stores this character, we would actually find this. So these are 4 bytes that store this character. The bytes are 00080. And if you remember, in this big Unicode table that we have, this is actually the entry for identifying the number of the character in that big table. So if you go to that table to row number 80, you will actually find uppercase P. That's where that is, right? So you can think of it as a direct matching of between the number that is stored at byte level and also the number that it represents in the Unicode table. OK, so mystery solved. We know Python stores characters as 4 bytes. This is a 32-bit integer. In Python, we don't really talk about fixed size integers because integers are just any size you want. If you're programming in C or something like that, that matters quite a bit. So this is what Python does. Now, if you think this is like the whole story, we've solved everything, you should be a little bit skeptical because what about files, right? So like Python can decide to do anything it wants in memory, but when we're dealing with files can be produced by any number of different programs. Python has no control over that. So if you look at a file, again, the thing to remember is like the bytes are the actual content of the files, and then the text, the strings, are the interpretation of the bytes. So one thing we could do, we can kind of try to guess what's actually, the string that's in the file. How is it actually stored? So what we've done here, we've tried to match up sort of like 1 byte to 1 character. So we've said first byte is the number 61, and that's going to correspond to the equal sign. And then this was actually my outline for this talk. Then the next byte is the number 32, that's a space. And the next character is 83, that's going to be the S. And so far, like this one-to-one matching seems to work out. Now, this isn't really conclusive proof that that's the exact correct scheme for decoding this, for interpreting this file. It could be that there's something later on in the file that would invalidate this approach and would show that this is actually not correct in the file, in the whole file. But at least so far, it seems to be working fine. And of course, this way of storing characters, one character stored in one byte, we call Ascii. So we're all familiar with Ascii. Ascii is one of these things that have been around in computer science longer than most of us have been. So was introduced in the 60s. And in Ascii, we use 7 bits to store all the possible numbers that will then represent the characters that we want to represent. So with 7 bits, we can store 128 characters. At the bit level, this is what it would look like. So the first bit would always be 0. It's not actually used. And then these bits would actually store the number that you would then find in the ASCII table that corresponds to the number that we give to the character. So again, we have the character, which has the number 80, which is stored like this in bits, and stored in 7 bits. And now you might think this is actually not that many characters. It's still quite useful because we can represent the whole English alphabet, both in uppercase and lowercase. We can represent all of the digits, 0 to 9. We can represent a bunch of punctuation signs like plus and minus and exclamation mark and so on. There's also a bunch of things that we call sort of like non-printable, like control characters in ASCII. Even things like space and new line are not, you could think of them as not really characters in the sense that you don't actually write anything. It's more about like skipping and leaving space. So that's ASCII. Obviously, compared to Unicode, there's like much fewer batteries included in ASCII. And also like even the name is kind of sounds quaint, like the American Standard Code. These days, we're kind of used to anything related to computing is really international. And then why is this American? It seems very sort of localized, right? So to overcome the limit of ASCII, a lot of people had this idea of like, why don't we use 8 bits instead of 7 bits? I mean, the 8-bit is there already. Why don't we just use it? If we extend the range of characters from 128 to 256, that gives us a lot of new characters that we can store. It would be convenient to keep the first 128 characters the same as in ASCII. That means that if you had files that happen to only use the first 128 characters, they would work fine with programs that kind of assume the world is ASCII. So that's a nice benefit to have. And then with the extra 128 characters, we could actually add a lot of extra characters. So like if you wanted to write Italian, a lot of the characters could be represented with ASCII, and then you could add a bunch of like accented characters within the additional 128. This would be quite useful. So a lot of people had this idea. This is a partial listing of the various encodings that are used to encode 8 bits as a character. There are many more than this, but basically the two most well-known ones is, first of all, you have the ASCII standard, the ISO standard, the ISO 8859, which defines a lot of these extensions, the -1, -2, -3, and each of these extensions corresponds to like a family of languages. So like -1 would be like Western European, -2 would be Central European, and so on, all the way to -16. And then Microsoft introduced its own character sets, which are the Win, kind of for Windows, and has its own numbering system, and they are very similar to some of the to some of the ISO extensions, except there are some differences. So you can't really interchange them painlessly. And so under this encoding scheme, again, the first 128 numbers are the same as ASCII, and then anything upwards of that would be different. So like here's the byte. So we see the byte which has a number 163. Under the different encoding schemes, it represents a different character depending on which encoding set you use. So you see all of these different 8-bit encodings, and you might think, well, I'm not sure if this is really such a good idea, because now we've defined all of these different, mutually incompatible standards of interpreting the same 8 bits. Isn't that going to lead to some problems? But what I want to point out is that this was actually a pretty good solution at the time. So like today, we think of computing as this really international thing. Everyone is on their smartphone, connected to the internet. If you think about like the world in the 80s and maybe even the 90s, if you're like an Italian software company and you made software that was used in Italy, then the files that were produced by your software actually would be compatible with other software made by other Italian software makers. So if only you could agree on one encoding to use sort of at the national level, this would work quite well. So it's not really an international solution, but it is a good national solution. Now, obviously, one limitation of that is you couldn't mix like characters from one of the sets with characters from another. So you couldn't write both like Italian characters and say Russian characters in the same file. You would have to choose. And then the internet became really popular. So now it's kind of, again, sort of changed a lot of assumptions, because now it became really likely that you would have a file that was produced on a computer in one country, which was then sent over the internet and opened by another user in another country. And the question is, when the file is opened, will it then be displayed correctly? So we're going to try to simulate this situation. So we're going to try to create a file as if it were created using, let's say, Russian software. Then we're going to transfer it to an Italian user, open it as if we're using sort of Italian software. So this is a string. So this is basically, I don't speak Russian, but I copied this from Wikipedia. So this is 2 words in Russian. We're going to encode it using the ISO-5, which makes sense for Russian because it contains the Cyrillic characters. We're going to then pretend we're sending the file somewhere else. We decode it as ISO-1, which would be used for Italian, for example. And then we get, the characters back. So this doesn't look like Russian, doesn't look like Italian, doesn't look like really any language that I'm familiar with. Now, it looks like the data has somehow become corrupted, but that's not true because, we sent 18 bytes, we received 18 bytes correctly. It's only that we couldn't kind of figure out how to interpret the bytes. And so the whole problem is that we've used the wrong encoding. And so this really sort of illustrates the need for having a character encoding that's truly international. Okay, so we started talking about Unicode. Unicode came out in the 90s. It took a while for it to become really widespread. But sort of the basic idea behind Unicode was like, well, okay, don't worry so much about the 7 bits or the 8 bits. Let's just use as many bytes as we need so that we can represent any character basically within the same file, within the same stream of bytes. That maybe doesn't seem like such a big difference, but it did break some assumptions that people were kind of used to making before that. So in a world where one character is 1 byte, it sort of simplifies a lot of things. If you want to do something like check the length of a string, if you say, okay, I have 18 bytes in the string, and therefore I have 18 characters, like there's nothing more I need to do. I don't need to like traverse the string and count or anything like that. I already know that. Also for I/O, it's quite interesting because I/O always operates on bytes. So if you're reading from the network, if you're reading from disk, there's no chance that you will get like only the first 3 bits, but not the last 5 bits. You will always get the whole bytes. And again, so if a byte is a character, then you can say, okay, this is a character, this is a character, this is a character, as you're reading the stream. Now, in a world where a character is represented in multiple bytes, it's a bit trickier because now, if let's say you're reading the stream of bytes and part of it is like corrupted, or you're catching up reading the stream and you're not reading it from the very beginning, you're sort of starting to read it in the middle. Now all of a sudden you don't know, is the byte that I'm looking at, is that the beginning of a character? Is it somewhere in the middle of a character? It's sort of much harder to figure this out. Okay, but anyway, we've agreed we're going to use Unicode because Unicode solves all these problems that we had with the different 8-bit character encoding schemes. So we're going to try to consider our options we have. Even though we're using Unicode, there's still multiple different ways of doing that. So we're going to encode this string of 4 characters, so it's just a normal P. Then you have an Arabic character. Then we have the accented E, which is used in Italian a lot. And then we have a Chinese character. So under different encoding schemes within Unicode, so the UTF-8 is the Unicode transportation format, this would come out very differently. So if we go for the simplest variant first, that would be UTF-32, which would be just saying, don't worry so much about it, just use the same number of bytes for every character, and then that way we keep it simple. So you can see each of the characters here have the same number of bytes, and that just makes it kind of quite predictable. You could say, well, maybe this isn't really necessary. Maybe if we use 2 bytes per character, which would be UTF-16, then we could store numbers up to 65,000. in either case, a lot of the characters that are most commonly used would fall within that range of the first 65,000. So we could store almost all the characters in 2 bytes, and maybe some characters we would have to store as 4 bytes. And finally, you have UTF-8, which is by far the most sort of pragmatic approach that says, okay, the number that we're going to store, which is the number that corresponds to the number that the character has in Unicode, we're just going to use just as many bytes as necessary to be able to store that number. So that could be for small characters, for small numbers, this could be 1 byte, and then anything up to 4 bytes, depending on how big the number is. So in UTF-8, obviously, no longer is it the case that one character corresponds to the same number of bytes. It's now different. So this one has 3 bytes, the other ones have 2 bytes, and the first one is stored in 1 byte. It's not really obvious which one of these strategies is better. From the point of view of a programming languages typically like to say that each character is stored in the same number of bytes, because that makes certain things easier. If I say, give me the 3rd character in the string, you can say, okay, I'm going to skip the first 4 bytes and then the second 4 bytes, and I'm going to start reading here, I'm going to read 4 bytes, and then that's it, I'm done. So I can actually just jump right in here and just read this, and then that's all I need to do. Whereas if I want to do the same thing with UTF-8, I don't know where this 3rd character actually starts, so I have to start reading from the beginning, and then and counting characters until I find it. So now for the purposes of storage, we typically want to be as efficient as possible. So if you kind of look at this encoding of UTF-32 with a sort of a critical eye, you can see that a lot of these bytes are actually 0, and it doesn't seem like they're really contributing that much to being able to represent these characters. So for storage and for transport, UTF-8 has kind of become the de facto standard, whereas internally in Python at least, UTF-32 is used. I should also mention this has changed a little bit over time. So like programming languages that have been released more recently, like Go and Rust, they've just decided we're just going to use UTF-8 internally, because now a lot of the time we're going to read bytes from the network, and then we have the same representation on the network and the same representation in memory, which means we don't even have to do any conversion. It's really convenient that way. And as for sort of making string operations a bit more expensive, well, turns out maybe it doesn't make that much of a difference anyway. So it's more the sort of the pragmatic approach. Okay, so back to Python. So first we're going to look at Python 2. And because of dealing with bytes and all the problems you can have with like the bytes being encoded in different encodings, and you may not be able to easily interoperate them. One piece of advice that you hear very often is just use Unicode strings internal in your program, and then all the operations you're going to be performing on Unicode strings, and that really simplifies your life. This is good advice, so we're going to try to follow that advice. So we're going to open a file, and we're going to read all of the content of the file into this variable content, which now has the type str. Except that str is not of the type Unicode, is of the type bytes, right? It's a byte string. So we're going to try to convert it to Unicode. And we found the function has a very promising name, Unicode. We're going to try to pass the bytes into it. And then we hope this works, but unfortunately it turns out it doesn't work. And so what Python is saying here is that I'm trying to use the encoding Ascii to interpret the content of these bytes and turn them into Unicode. But what I've discovered is that I have a byte in this stream of bytes which exceeds the range of bytes that are permissible in Ascii, because in Ascii you can only have bytes from 1 to 127. Otherwise, it doesn't fit within the 7 bits. So this is what Python is saying. So unfortunately, this didn't work. We could say that, well, maybe this was overly optimistic. We were kind of hoping that Python would somehow do this conversion for us without even knowing what the encoding of the bytes was. What if we just tell it? It's part of the Zen of Python, be explicit as opposed to just making assumptions. So you could also pass the encoding explicitly to this Unicode function. That seems like this would really work, except that what if we don't know what the encoding of the bytes is? So this is a pretty common situation that you've probably come across. You have a file, you don't actually know what the encoding is, and then the question is, well, what can you do? Can you just guess what the encoding is? Unfortunately, you cannot, because as we saw with all of the different 8-bit encodings, these are all ways to interpret the same 8 bits differently in an incompatible way. And so there's no way that you can just successfully guess what the encoding is. in certain cases, you can try to look at the file and sort of like we did and interpret it. But in the general case, you can't really solve this. So if you don't know what the encoding is, you're stuck. So you might say, OK, I'm going to be very careful that every time I'm dealing with a file, I know what the encoding is. And I'm just going to like be very thorough in that part of my program when I'm reading the file. And then afterwards, I'm just going to use Unicode in my program. And this problem is not going to affect me at all. OK, that would be nice. It turns out that that's not always the case. So here we're trying to do something that seems very innocent. We're just trying to concatenate two strings. So the first one is the string Python, which is a Unicode string. And then the second string is actually a byte string of 2 bytes. And we're just trying to concatenate them. So like, what could go wrong here? Now, unfortunately, we get the same error. So what Python says is like, OK, I have a Unicode object, and then I have a string object, and I want to perform an operation that combines them. But they're 2 objects of different types. So what I'm going to try is just convert this object to the type of the other object, convert the stir object to a Unicode object, and then I'm going to perform this operation. And then it finds out that, oh, there are bytes here which are not valid within ASCII, and therefore I don't know what to do. I give up. So this is kind of painful because this is an implicit conversion. Like it's not kind of obvious that what you're trying to do is convert anything. You're just trying to do a concatenation, and yet you still have this problem. So in Python 2, these implicit conversions are kind of everywhere. It's kind of a painful experience because a lot of the time you're writing some code, and you think to yourself, I don't have any Unicode versus strings problems here because this code that I have doesn't actually do any conversions. It doesn't try to convert anything. So I don't have to worry about that, or at least in this part of my program. But it's the case that anytime you pass like a Unicode object into a context that expects a stir object, Python will try to convert it for you. And anytime you pass a stir object to a context that expects a Unicode object, Python will try to convert it for you. And it will always do this using what it's called the default encoding in Python. So here you can look up what it is. And it's typically set to ASCII. So all of these conversions will happen implicitly using ASCII. And then you will see these well-known exception types, Unicode encode error, Unicode decode error, kind of in code that you wouldn't expect to see this in. Now, there's kind of a final pain point here, which is that if you have a program that deals with data that's supplied by users, so let's say this is a web application, and your users are supplying the data that flows through your program, if all of the data that your users happen to use just is ASCII, for whatever reason, maybe it's only like English-speaking users or something, then all of these conversions will happen implicitly, and they will always work. And it will seem as if your program works perfectly. And then, all of a sudden, you have a user who maybe has like a name with like an accented letter in the name or something like that, and all hell breaks loose because all of a sudden you start seeing these errors, and it makes you sad. So, if you think this is kind of a bad state of affairs, then you kind of agree with the Python 3 designers because they said, maybe this isn't the best design, maybe we should change this. And so in Python 3, basically the big new thing is we're not going to do these implicit conversions anymore. So that's Python 3. If we try to do the same example with the concatenation in Python 3, again, we have a Unicode string, and then we have a byte string, and we're going to try to concatenate them. And Python says to us, Python 3 in this case, says to us, well, you're giving me a Unicode object and a stir object, and you want me to combine them, but they're 2 objects of different types. Like, what do you want me to do with this thing? Like, you fix it. I'm not going to try to figure out what to do here. So it just completely refuses to do it for you. This is where things got a bit complicated, because in Python 2, we had like 2 forms of strings. We had byte strings on the one hand, which is to say like 1 character is stored in 1 byte, and then we had Unicode strings. So for a long time, we were kind of used to do handling strings this way. For byte strings, we had the stir type, which is actually a string of bytes, and we would write the character in quotes, and that means 1 byte, which represents that character. And then on the Unicode side, we had a type called Unicode, and we would write it, again in quotes, but with the U prefix, which makes all the difference. And this means we're storing this character in 4 bytes. And then I don't know how many of you have really been noticing this, but there was also a type called bytes, which is actually just an alias for stir. So these 2 things are exactly the same in Python 2, and you can use them interchangeably. And then in Python 3, it became sort of confusing because the type that we used to use all the time, which was called stir, all of a sudden in Python 3, it just disappeared. It's not there anymore. So now if we want to store byte strings, we have to use the bytes type, and we have to use the B prefix, and we still get the same result. So we still get one character stored as one byte. Whereas on the Unicode side, we used to have this type called Unicode, which all of a sudden doesn't exist anymore. That's pretty surprising. And now instead, there's a type called stir, which has kind of taken its place, except it's a completely different stir than we had on that side, because now this means this is a Unicode character. It's stored in 4 bytes, and it's like it doesn't have the same meaning anymore. So all of the programs that you already had that were running on Python 2, now the question you have to ask yourself is, if I change this very fundamental assumption that this character is now 4 bytes instead of 1 byte, will all of my code work exactly the same, right? Probably not, or at least maybe not. That should kind of explain the whole deal with porting from Python 2 to Python 3. This is like the main fundamental difference between the two. So we tried to do the file reading example again. So we open the same file, we read it, the code is actually the same. We read all of the content of the file into this variable content. It still has a type stir, except now we have to remember stir is now a Unicode string, not a byte string anymore. And actually this seemed to have worked really well, because we wanted to read bytes from a file, we wanted to read it into a Unicode object, and we've actually accomplished that. And so, like, what happened? Did Python somehow guess what the encoding is? It seems to have just like completely solved the problem for us without us having to do anything. It turns out that if you try this example and you try to read a file that just has a whole bunch of random bytes, sooner or later you will discover this. So you will have this. Trying to use UTF-8 as the encoding. So you say, aha, so Python is still making an assumption about the encoding of the bytes coming from this file, except now it's using UTF-8 instead of ASCII. And I found a byte, which is the FF, which is another way of saying the number 255, which isn't valid in UTF-8. So I don't know what to do with this byte, because clearly this is not UTF-8, the thing that you're giving me. Now, if you had tried to use the encoding ISO-1, this actually would be valid, because the byte 255 does actually represent a character under this encoding. So like the fundamental problem hasn't really changed. We still need to know what the encoding of the file is, and Python 3 doesn't somehow magically solve that for us. It's just that now it assumes UTF-8 is in use, much more so than ASCII. Okay, so we've learned all these things about how characters are stored and the differences between Python 2 and Python 3. So we're ready to do some troubleshooting. So all of these examples actually work the same across Python 2 and Python 3. So you don't have to worry so much about the exact version. So the first one is we're trying to read some input which has really just one character. It has the accented E character. And we're representing it as 2 bytes. So it's one character stored as 2 bytes, and we're trying to decode it from bytes to Unicode using this ISO-1 encoding. And what we end up with is a Unicode string that has 2 characters, except it doesn't look correct because neither of them is the character that we wanted to have. So you've probably seen this example before, and like by accident, I mean. And so what's happening here is that we're trying to decode a single character, but we're using a character encoding that treats each byte as a character. And so at the level of bytes, this is happening. So you have 1 byte 195, 1 byte 168. Each of them is then converted to its own Unicode character, and we get these values for that. But, and even though that works, this is completely not what we wanted. This is not what we intended. And so the problem is we're dealing with an encoding that treats a single character as multiple bytes, but we're using an encoding to decode it that treats each character as 1 byte. That's the whole problem here. So if instead we pass Unicode, if we pass UTF-8 as the encoding to use, we get 1 Unicode character, and it is actually the accented E, which is what we wanted. So this does actually work correctly. So now we're taking each of the 2 bytes, we're combining them into 1 character, 1 Unicode character, which is the accented E. So this actually works the way we wanted. So here we're going from bytes to Unicode. Now we're going to go the opposite way. So here we're passing a sentence, short sentence, which is a Unicode string, and we're passing it to some function. We don't really know what this function is doing. We didn't write this function, but what we know is that what we get as a return value is actually a bytes object. So we know, okay, a conversion must have taken place. And all of the characters in the string seem to be still the same, except for the one character, which was the accentity, which is now replaced with a question mark. So if you're seeing this behavior in code that is like a library or a code that you didn't write yourself, this might seem kind of confusing. Now, what probably happened is someone was doing this. They said, I'm going to encode the Unicode string to Ascii. And then because we're going from a Unicode, which is this whole big character set with over 1 million different characters, to Ascii, which is this much smaller character set with only 128 characters, it's actually pretty likely that there will be characters in the input that are not representable in the output. And then we say, okay, if that's the case, we're just going to replace them with this placeholder character, which is the question mark. And that way, the conversion from Unicode and Ascii does still succeed, because if we hadn't passed this replace parameter, this would have just thrown an exception. So it does still succeed. And if we're trying to print this, say, write it into a log file or print it on the screen, we at least get something that's kind of usable, even though it's a little bit corrupted, right? Because we've lost some information. So a sort of very similar case to this is where we pass the same string, Unicode string, to some function, and now in the output we can say that, oh, the character which was not representable in Ascii is just now completely gone. It's just not there. So probably what happened was this. So someone was trying to encode the Unicode string into Ascii, and then saying, well, if there are characters here that are not representable in Ascii, I don't really care. Just discard them. Just drop them. Don't even include them. And so now this string is not even the same length as the string that we started from. Okay, another example of something that went a little bit wrong. So here we're trying to do something different. We're trying to just print some bytes to the screen. And so these are the bytes we're printing, 255, 254, 253. And we can kind of see that the result of that doesn't seem to be correct, because we're getting 3 times the same character, even though these bytes are different. So whatever character was supposed to have been displayed clearly isn't correct here. So something must have gone wrong. Now, there's no conversion happening here. There's no Unicode string that we start with that we have to then convert to bytes. We're already using bytes. So what happens is the Python interpreter says, okay, I'm going to print these bytes, which means I'm going to write these bytes to standard output. And then the terminal program in which I'm running the Python interpreter says, okay, I'm connected to the standard output of the program that I'm running, which is Python, and I'm receiving bytes, and it's cool because I know how to display UTF-8 bytes. And then it turns out that it receives some bytes which are actually not UTF-8, and all of a sudden it says, oh, I don't know how to display these bytes, so I'm just going to use this placeholder character. Now, if you're asking yourself, is it weird that this is the result? Shouldn't I expect to see like an exception raised here? Well, if you think about it, that would actually not make sense, because from Python's point of view, everything is fine. It's just writing bytes into a location in memory, and it's the terminal program that's having a problem to not being able to display these bytes. So there's no way for the terminal to say, hey, Python, you should raise an exception because I'm having a problem here. Okay, so that was the content. A few things to remember. When you see strings on your computer screen or on your smartphone or at the display terminal in the airport, you should always think to yourself, even though these are strings, they're actually numbers. And if you can keep that in mind, then it's going to simplify it much more for you and put you in a position where you can actually make sense of the kinds of errors that you're looking at and being able to fix them. So that's the real key here. And if you encounter problems with encoding or decoding, the best thing to do is actually look at the bytes that you're dealing with. So inspect the bytes. You can do this in the Python interpreter. You can also do this in a hex editor. Sometimes that's easier to do. And if you find that when you're just looking at bytes in hex, it's kind of hard to make sense of it, you can convert them to decimal. So I did that in this talk with all the examples. Just displaying hex in decimal makes it easier, at least for me, to be able to read it and make sense of what I'm looking at. And then a couple of things to keep in mind where you're actually inspecting the bytes. If in the stream of bytes you have bytes that are higher than 127, then you know that the thing that you're looking at isn't ASCII, because in ASCII, you cannot actually exceed the number 127, otherwise you wouldn't be able to display that in 7, you wouldn't be able to store that in 7 bits. If you have cases where you're trying to decode something from bytes, and it turns out that you're seeing multiple characters in a place where you only expected to see one character, this is really common for like people whose like names get displayed incorrectly as like 2 characters as opposed to 1 character with an accent on it or something like that. What's happening there is that in the input, you're dealing with an encoding that treats 1 character as multiple bytes. So it's a multi-byte encoding. And what you're probably using is a single byte encoding to decode that content. And therefore, you have this problem that you're seeing multiple characters, but all of which are incorrect, as opposed to the 1 character that would have been correct. And finally, one detail about UTF-8, if ever you see the bytes 254 or 255, this would be FF or FE in hex, then you know that the input isn't UTF-8, because these are never valid under UTF-8. Okay, so that's the talk. I would be happy to take your questions now. Should we wait for the microphone? Oh, it's one back there.
So you said that Python 3 uses UTF-8,
Uses UTF-32.
1 byte for transport and stores in 4 bytes?
No,
Is
so
that what you said?
when I say transport, I mean that's not a concern that Python has, what the transport format is. When I say Python, that has to do with what Python does internally and when it's storing characters in memory. Yes.
What was the other question?
One here, I think.
There you go.
How does the UTF-8 encoding distinguish between the char boundary?
Okay,
Well,
that's a really good question. I thought of including this in the talk itself, but I scrapped it because I thought it wouldn't fit. So if you look at this example, this is the UTF-8 string. Now you might seem, so the question is, when we're reading UTF-8, how do we know that the first character ends here and then the second character ends here, as opposed to just, like, how do we know how big the actual character is? At the level of bits, UTF-8 has a certain structure, which is actually quite clever. It has to do with why UTF-8 has become so successful. That means that if you're starting to read a stream of bytes somewhere sort of in the middle, then UTF-8 pretty much guarantees that if you're looking at the first byte in a character, you can already tell how many more bytes you have to read to reach the end of the character. Whereas if you're reading a continuation byte, which is what it's called in UTF-8, and so it would be like this one or one of these two, then you know that you will have to read at most like 3 bytes this way or 3 bytes the other way to find the initial byte, and then you're synchronized, you're back up to speed. This is a property that UTF-16 and UTF-32 don't have, of being able to kind of find out where you are. So this is a pretty clever trick in UTF-8. Any more questions? There. If you just wait for the microphone to arrive.
So if UTF-16 doesn't have the thing that UTF-8 has that lets you find the first byte, how do you distinguish between 2-byte characters and 4-byte characters in 16?
That's a pretty good question. I don't think that if you're just looking in a random location in a file that you would necessarily be able to tell. If you're starting to read the file from the beginning, there will be, in UTF-16, what's being used is, instead of starting to write the content of the string right away, it will first write 2 bytes, which represent kind of like a hint saying like this is UTF-16. In UTF-32, the hint will be 4 bytes long. So you can, if you match on that, then you can find out, but that means that you have to be able to read the string from the beginning. If you start reading it somewhere in the middle, then you wouldn't necessarily be able to figure this out. Other questions?
Cool, thanks.
Thanks.